Okay, maybe we can get started. I think our rate of people increase has slowed down. So I'm very pleased to introduce Mark van der Laan, the professor of biostatistics and statistics at the University of California, Berkeley, and take it away.
All right. Yeah, thank you so much. And also for the invitation for this whole visit. I've met a lot of great people, postdocs, students, and faculty. So it was very nice. Yeah, so today's talk is about an advance within the framework of targeted maximum likelihood estimation I've worked on over the last years. And there is a reference for like a tech report on this topic. So the outline of this talk is I'm first going to explain what just regular TMLE is, of what I now then call in this talk first order TMLE. I show some exact property of first order TMLE, which shows a finite sample remarkable property. And the reason why I do that, because it generalizes to what happens in the higher order TMLE. I talk about the highly adaptive Lasso as a very powerful machine learning algorithm, which guarantees a certain rate of convergence we need for guaranteed asymptotic efficiency of estimators. Then I define this new second order TMLE, where again it has a finite sample exact property, but in particular it shows that it now starts having a remainder which is third order, while usually we work with remainders which are second order when you start using as approximation empirical means, so asymptotic linearity. So we'll make that formal. That's what this is, exact expansion. We can generalize it naturally to a k order TMLE, and then the remainder will be k plus 1th order. And I show some simulations and just how for certain problems like average treatment effect and another theoretical well-known problem of integrated square density, how this actually really changes things. And then some concluding remarks. And feel free to interrupt with questions. I don't have to finish this talk at any time, can easily stop, and there's no problem whatsoever. So firstly, I want to go back to how TMLE is all fits in this general framework, which I often think of as the roadmap for statistical learning, which is kind of common sense, but nonetheless sticking to it is not common practice. Let's put it that way. But in the TMLE framework, we do. And so what is that general framework? Is as a statistician, number one, you realize that your observed data is the result of an experiment. So you need to know about that experiment. You need to talk to your collaborators and understand how this data was generated. That means it's a random variable. It has a probability distribution. It often involves data on n units. And maybe you're willing to assume that these unit data structures are independent, identically distributed. Maybe not. It could be something else, a time series or whatever. Anyway, so that's step one. And that also allows you then to start writing down what are all the observed variables we observe, and how can we write down the likelihood of that, right? Some kind of joint density, and you maybe factorize it by time ordering, which is very typical. And so you get this product of conditional densities, and that makes up the likelihood of your data. And then you have to say, what do you know about that? What do you know about each of these conditional densities? And there you have to be honest. You have to be fair. In other words, if you know nothing, you know nothing. If you know something, like conditional independence, like whatever treatment only depends on 2 covariates because you talk to the doctors in your study who made the treatment decision, and they tell you, we only look at these variables. Great, that's huge knowledge. But that's conditional independence knowledge. That means the world of parametric models are gone. They are out of it because these are not models, because models are supposed to be, in this definition of statistical model, contain the true data distribution. That's the idea of a model. If you want to, other models you might call working models, but they are not formal statistical models. They should capture real knowledge. Then comes the next question: what are you trying to learn from the data? Right? We don't necessarily need the whole density of the data, the whole distribution. We only need maybe certain features of it. And so that's another big problem. How do you do that? And then, of course, you need to talk to your collaborators and know what the scientific question is. Maybe it's some kind of causal effect. Then you can use the causal language and causal models to come to an agreement. What is the real question of interest? with your collaborator, and then comes the identification problem of finding an estimate, a feature of the observed data density, which approximates or maybe even equals that causal question, the answer to that causal question. So that's a whole little exercise roadmap on itself, and that shows the power of the field of causal inference is really about generating interesting observed data estimates which approximate causal quantities the best it can. So that gives then a psi of P0, a feature of the data distribution, where P0 is the true data distribution. By now you have defined your statistical estimation problem, and now comes the question, okay, so now we are ready. What's going to be our estimator? What is an estimator? An estimator is an a priori specified algorithm which maps the observed data into a number. Let's say you're trying to estimate a real valued feature for simplicity. So that's like an R package. And so there is no game here. Estimators are not, an iterative playing with the data, human interventions, having discussions about it. That's not an estimator. An estimator is an a priori specified algorithm, one chance, that's it. And of course you want that estimator to be good. So you want it to have good properties. So you worry about its mean squared error, you worry about its bias being smaller than the standard error so that inference is doable. And once you nail that, you establish maybe that your estimator is approximately normally distributed, centered around the truth with some variance, which you can then estimate. Then you can construct confidence intervals, right? Because then you understand the probability distribution of the estimator minus truth, and you can do stuff. And so that's great. And that's in essence where it is. And then at the end, you have an interpretation step, which is really a sensitivity analysis, where you say, look, this is a confidence interval for the estimate, but that's not necessarily equal to the causal quantity. There might be a causal gap. You might want to acknowledge that in your final interpretation. And that's something else we have proposed, a non-parametric type sensitivity analysis, which is very easy to do and makes it all very transparent. Okay. So what is targeted learning then? Targeted learning just says, I call it here a subfield. I say targeted learning is a subfield of statistics concerned with the development of estimators of the data density based on your data and corresponding plugin estimates for your target features, such that you can actually come up with confidence intervals, which do have the right coverage as claimed, but all based on realistic statistical models, which are collections of data distribution, script M called here, which are of course going to be highly non-parametric. By necessity, if you want to do this, you will have to do adaptive estimation because there are no parametric models. So parametric maximum likelihood cannot be done. That is, gives you kind of an estimate, but it's not going to have any good properties. So we need adaptive estimation, and that's where naturally then the word machine learning starts coming up. But that's not an easy task to do data depth estimation, model selection, cross-relation, and then at the end still claim you have some kind of inference. I mean, that was for a long time, people thought that was not really doable. And that's why you need something on top of the regular machine learning, and that's called TMLE. So in this talk, we will focus on observations being independently identically distributed so that the data is all described, the likelihood is all described by the common probability density of your unit data structure. Okay, so what is TMLE? Is an approach for solving that estimation problem, these realistic statistical estimation problems, and it's a two-stage procedure. And so how does it work? It first says, okay, so your goal is to estimate a particular psi of p, and so the first thing you have to do is estimate the data density. Now, maybe your psi only depends on certain conditional densities in your factorization, so you only have to worry about these 10. The others you don't have to do. But nonetheless, there will be a bunch of conditional means or conditional densities you will have to estimate from the data to even evaluate psi of p. So that's the first task. How do we do that? That's where we call that the initial estimator of the data density. Now that's where I'm not going to dive into that in this talk, but that's where superlearner, of course, comes in as a powerful approach, which is able to utilize the world of machine learning and parametric models as well, and create a single algorithm which uses all of them, and then is more powerful than any of its ingredients by just being able to choose the winner among a competition based on cross-validation among all these candidate estimators, and then that's the one which will be chosen, and it can theoretically be proven to do a great job in doing that and actually be asymptotically completely equivalent with the best possible choice you could have done if you would have known the truth, namely grab the estimator close to the truth. Now that's remarkable, and that's, makes superlearner a very powerful approach for the sake of estimating these conditional densities and conditional means and whatever you need. That's great, but that is doing a trade-off for the sake of learning the whole function, the whole like conditional mean or something. So that's where, and that's getting the wrong bias variance trade-off if you don't really need the whole conditional density, which is like answering millions of questions, right? Because for a conditional mean, you're getting an answer for every input variable. So we are only asking for one number, one feature, psi of p, which is just a real number, like an average treatment effect. So you're somehow sandwiching that whole joint density into an operator psi of p and then map into a real number, which of course involves a lot of averaging over the overall density. So that's a much smoother parameter, as we say. It should be able to estimate that with a variance of behaving like 1 over sample size. And the machine learning algorithms will, get some rate of convergence, maybe n to the quarter or something. But even when you plug it in there, that still carries over all that bias. So it wouldn't, generally speaking, wouldn't work. So that's where TMLE comes in. So what's the idea of TMLE? That says, okay, why don't we create a parametric model which uses offset the initial estimator, has a parameter epsilon, just like a theta, right? We call it epsilon. We call it the fluctuation parameter, which means when epsilon is 0, you get back your initial estimator. But as epsilon moves away, you stay in this class of densities in your statistical model, and you move away in a certain direction. So you have this kind of path in your model space. And then you say, let's do MLE, just like parametric maximum likelihood. And that's what this step is, this maximum likelihood step. And then you get your update. And that's the TMLE update. Of course, the key is here, what path are you going to use? Right? There are many paths, many parametric models. Typical, from a first order perspective, what you care about for a parametric model is its score. So that's kind of the direction of a parametric model, at least in a local sense. And so that's what you need here is you need a parametric model which has as score the so-called canonical gradient. What is that guy? That's something you calculate from your target estimate. Your target estimate is a function which maps data densities into a number. You can compute derivatives of that. Pathwise derivatives, they're called. So you take a parametric path through p, it's like psi p epsilon minus psi p divided by epsilon. Let the limit go to epsilon 0 and write it as some covariance of some function with the score of the path. That's called pathwise differentiability. And that function you then get is like a gradient. And then if you do it right, it's the canonical gradient. Now, that's a unique thing you can calculate mathematically by knowing your estimate. What's key about that, that gives you the direction of the path along which this target estimate will change maximally. So, and in fact, you can think of it also that along for every unit increase of the likelihood, when you move away from your offset in the direction of increasing the likelihood, for every unit increase in likelihood, you get the maximal change in your estimate. So it's like every likelihood increase is immediately 100% translated into a change in the estimate and thereby moving in that direction of the truth. And that path is now defines then the TMLE. It's called the least favorable path. You can make sure that it does not only have the right score at epsilon is 0, but even at any epsilon. So it's always going in the right direction of steepest change in the estimate. And that's called a universal least favorable path. Then in one step, you're done. And then because this is an MLE, it solves a score equation, but the score equation of the log likelihood is nothing else than the empirical mean of the canonical gradient, because that's how it was done. So at the end, you solve the empirical mean of the canonical gradient. So you solve this equation, estimate equation in your TMLE update. And that's very key. That's a very important score equation. It's the right score equation to solve if you care about your particular estimate. And then the plugin estimator is done. That's the TMLE. And that's the whole story. So that's a very general template you can do for any statistical estimation problem. Okay. So how do you analyze a TMLE? It's kind of remarkable. I remember when in the beginning, when I would give these talks, people were very upset. They said, no, you cannot do machine learning. That doesn't work. I know that from maximum likelihood. You cannot do that. You get irregular estimators and so on and so on. The reality is it's a one-page proof. It's really very transparent. And it's not like something we're hiding. It's just very transparent. So let's see how it works. So there are two things. The first thing I do when I have a particular problem, I'm not only calculating the canonical gradient, I'm also calculating this exact second order remainder. I call it R1. And it's defined as for any P and P0 as psi P minus psi P0 minus this first order linear approximation, which is the P minus P0 applied. So it's the integral of this, right? Of this canonical gradient with respect to P minus P0. It's just empirical process notation. That will be second order because this is a first order difference. And then of course, what's left is some second order difference in the P minus P0. So we can calculate that for any problem. And by definition, you can then already say, right, firstly, this P is 0. So what we get then, we can apply this definition at P being the TMLE. So you get psi TMLE minus psi P0 equals minus P0 applied to the canonical gradient at the TMLE plus the exact remainder at the TMLE and that. So this is already starting to look nice, right? TMLE minus truth is what we want. And now we want to get here something like, oh, but that's easy because we know the empirical mean of the canonical gradient equals 0 at the TMLE. So let's add that here. So now we have this exact identity for the TMLE, which you will see in every paper we write, is that plug in TMLE minus psi P0 is the empirical process, Pn minus P0 applied to the canonical gradient at the TMLE plus an exact remainder. So you're almost done now. Right? This is almost like an empirical mean of independent mean zero random variables, except this is a random function. It's not yet at P0. So you need a little bit of empirical process theory. And then here's the remainder, which is second order. So if your initial estimator is n to the quarter rate of convergence, so if you do a good job with your superlearner, this will be small and n to the minus half. And pushing this with a little consistency condition and an empirical process condition, which actually will be true for the kind of estimates we're talking about, because there's huge Johnson classes available, like all cadlag function of bounded variation. Then you get TMLE minus truth is the empirical mean of the canonical gradient at this P0. Now it's a fixed function, the fixed transformation of OI for every subject is a sum of independent mean zero random variables, and we're done. And we can do inference, obviously, right? So, and then actually, if you do the theory of efficiency theory, it tells you there is no more efficient estimator available. The moment it's asymptotically linear with influence curve the canonical gradient, which is what this guy is, you're done. You're asymptotically efficient. That means among all regular estimators, there is no estimator better than this one from an asymptotic perspective. So that's the whole proof. So let's do a quick ATE problem. So O is WAY. You have covariates, binary treatment, let's say binary outcome. You have n IID observations. And your parameter is, suppose we want to estimate the mean of Y1, which is this, the mean of a counterfactual Y1, what you would have seen if everybody would be treated in your population. And of course, you might care about the mean of Y1 minus mean of Y0, but it's all the same. So I'm just focusing here on one of them, which is the mean of Y1. And if you then go through the roadmap of causal inference, the identification result says that you can approximate the mean of Y1 by this statistical estimate. The mean of Y given A is 1W and an average. So this is the prediction of death under treatment for every member in your population and then average over the population distribution. And this will equal the counterfactual mean you would have observed if everybody in your population would have been treated if the no unmeasured confounder assumption holds. And so, we are going for this as our estimate, let's say. You figure out the canonical gradient. Here's the canonical gradient. You just have a feeling for what that looks like. It's a function of O, WAY. And of course, it will depend on where you do your canonical gradients, at what P. And you see it involves outcome minus conditional mean of the outcome multiplied by this indicator of being treated divided by the propensity score. And then here is some prediction for every W of the death under treatment minus the average of death, which is our parameter. Now you can think of if you see this, you see that this is actually a score of Y given A and W, the conditional density of Y given A and W. This is just a function of W. Now we will use the empirical mean over W, so this will always be solved. So that's why we don't have to target the distribution of W estimator because it's already a non-parametric maximum estimator. So the only thing you really worry about is this one, that you want the empirical mean of this to be solved, which means you will start adding a clever covariate indicator, over the propensity score to your offset, like your initial logistic regression. And then the score of that, from which we know from logistic regression, is nothing else than the covariate times the residual, and you get precisely this. So this tells us how to do a least favorable path I discussed. Now you can also calculate the exact second order remainder. It's nothing else, as I promised, it will be a product of two differences, and yes it is. Integral outcome regression minus true outcome regression candidate propensity score minus true propensity score divided by the propensity score. So this is two differences multiplied. We call this also a double robust remainder because it has this cross structure that if one of them is 0, the whole thing is 0, which is particularly nice in randomized trials because then this will be 0 because G is the propensity score, it will be known. And so there wouldn't even be a remainder. And then of course, that's phenomenal. And as I said, now the TMLE is inspired by the canonical gradient. It was nothing else than running a logistic regression with offset the initial estimator with a clever covert. We do the MLE step that gives us the updated outcome regression, and then we plug it in. And so the final plug-in estimate is the empirical mean of the targeted predicted probability of death under treatment for every subject in your sample and averaged. And that's the plug-in estimator. So the first order TMLE has this property, so I want to point that out now. So you could say, suppose I define for a given P, psi of P minus psi of P0 minus the empirical mean of the canonical gradient. This is the best approximation you're aiming for. So the question is, how would you like P to be so that psi of P minus that this becomes very small, right? So that's like really what your goal would be to how you would estimate P. So suppose I say, yeah, let's just play an oracle game as if, I'm in the world where I know everything. So I'm going to define this as my thing, and I'm just going to square it, and I want to optimize it in P. Now, by the way, look at this exact remainder. It can be rewritten, and you can see it involves precisely these very important remainders. It's the exact remainder you see here. Here you see an empirical process term you'll have to deal with in an analysis. And here is how you have to solve the empirical mean of the canonical gradient, which is another thing you have to worry about. So it's exactly all the terms are in there which are important. Suppose I say, okay, let me find the P which succeeds in minimizing this. So let's square it and P. So how would you do that? How would you come up with an algorithm optimizing this exact remainder? Now, normally you can say I'm using a steepest descent algorithm. I start with an initial P, like a Pn0, and then I'm going to construct a path along which this is the steepest goes down. And then for that, you need to know the canonical gradient of this guy. But the canonical gradient of this quantity, right, is nothing else. Look at it, it's just psi of P, right? Except there's a 2 in front. So what you get is that the canonical gradient of this guy is the same as the canonical gradient of our target parameter up till this scalar, which is just about which direction to move. So what we learn from this is that when you run the TMLE algorithm, which is just moving along this path of steepest descent, precisely this, you're going the same path, and in the direction will be right because you're going the right direction. So you're actually just carrying out a steepest descent algorithm for actually minimizing this term, which is kind of crazy. The only thing is it has to stop the moment the likelihood is maximized. Then it has no sense anymore which direction to go, and that's where it stops. But up to that point, it is literally just going for optimizing this exact remainder. So that's a finite sample feature of TMLE. Now you can actually show that in like here you see an integrated square density problem where you estimate the integral of the square of the density. It's a theoretical problem in theoretical statistics, which has been looked at by many people. So you might say, okay, let's do the TMLE for that. You do that by doing an initial estimate for the density, and then you do your least favorable path, which is defined by the canonical gradient, which is just this guy here. And you just start moving along, right? With a universal path, you would take very small steps, epsilon, and every time update and do it again. And so that creates now a single path in the density space, always moving in the direction of the canonical gradient, and you do compute and you track the likelihood till it's maximized. But here's then what happens in a simulation or in a single data set, fixed data set. This is not an average. This is a single data set. You start with an initial estimator and you see, and here's the truth. Here's the truth. And you see that it starts moving in the right direction every little step till the likelihood is maximized, and that's where it stops. And that's then the first order TMLE. So one thing when you when you think about the TMLE, right, we talked about the main condition, really the only condition, was that the exact remainder, the second order term, had to be small and n to the minus half. That required that somehow the superlearner is getting this rate of convergence n to the minus a quarter. However, the superlearner is as good as best choice. So we need at least one choice in there which has that guaranteed rate of convergence. So that's pretty limited. Most of the machine learning algorithms have little theory. They don't have much like any rate of convergence, and there are some abstract results about neural networks like n to the quarter, which which is borderline. So we really need an algorithm which gives us that rate of convergence. So that's what we did with the highly adaptive lasso. So what's the idea there? That we say any function of, let's say, d variables, x1 to xd, can be written in this representation. And this is nothing else than an infinite linear combination of this basis function. This is an indicator. It's a function of x, and it is a knot point u, and it is the indicator x bigger or equal than u. But notice x is multivariate, so this is a product of indicators. So this is like a tensor product of indicators, which are functions which go from R0 and jump to 1 at a knot point, like mu1, mu2, and up to mu whatever. And so this, and then this is just the increments of the function. And then so the increment of the function at that knot point multiplied by the indicator over all knot points, right? The whole area, the whole unit square is then summed over. And then you can prove that any function of x, which is cadlag, right continuous, left-hand limits, can be written in this way. Now, there's a little thing here. This is just a very nice short notation, but the reality is this integral also goes over the edges at 0, and that's where this is defined as the measure generated by the section of f, where the coordinates are set to 0, which are, of course, true, and only think of it as a measure in the remaining coordinates on the edge. So this involves, becomes really a sum of integrals, including an integral from the left open 0 to 1 over the full dimension, but also lower dimensional integrals over the lower edges. So when components of a knot point u are 0, which happens on the edges, like when one edge is that x1 is 0 and others that x2 is 0, then this bivariate indicator, this tensor product 2 indicator, becomes just a single indicator, right? So you see really what we are doing here is nothing else than writing a function as a linear combination of indicator x1 bigger than knot points, indicator x2 bigger than knot points, and then finally also the product of the two across pairs of knot points. And that can be generalized to any dimension. So the variation norm of a function, which is how much its measure is summing up over all the absolute value of the increments, is nothing else than this, right? So this you can think of as a coefficient, and this is now an L1 norm. It's just the sum of the absolute value of the coefficient. So, and this is we often call this the sectional variation norm, but it's really a measure of complexity. So what we conclude is that any function f, which is cat-like, is an infinite linear combination of tensor product of indicator base function, which is also called zero-order splines. And the L1 norm of its coefficients is actually the variation norm of the function. Oh, okay, it moved too fast. Okay, so that was this. And so now you can say, okay, what am I going to do is I'm going to define an MLE. I'm going to maximize my empirical mean, let's say of the log likelihood, or least square, sum of squared residuals for simplicity. If you do regression, and I'm going to minimize over all functions, except one constraint is that its variation norm is smaller than a constant. And then we can measure, we can select that constant with cross-validation. But suppose we approximate our function, which is an infinite linear combination, by a finite linear combination, which of course we can do because it only depends on the data. So at the end, you can find a finite set of knot points, which matters. And it's, in our case, we have specified like n times 2 to the power d of such points. And so then this candidate f becomes just a linear combination of these indicators. So it's like a linear regression model. And you just say, I want to optimize over all the beta now. It's a very large, so now it's like sum of squared residuals, so it's like least squares, but over a huge linear model under an L1 norm constraint, because the L1 norm of beta is the variation norm. And then we are back to doing the lasso. It's like GLMnet, that kind of stuff. And so that's the estimator, which we call the highly adaptive lasso. And of course, we can apply this to any kind of nuisance parameter we might need, like a mean of y given a and w or propensity score. And at the end, it becomes just high dimensional lasso regression. We also do it for conditional hazards, conditional densities, and so on. So this estimator has great properties because you can show that if you look at the so-called loss-based dissimilarity, you look at this is the risk, right? It's the best possible mean squared error if you do squared error loss. You could have obtained with the true function. You compare it with what the estimator achieves. This difference is actually real distance, square distance. It would be like the integral of fn minus f0 squared averaged. So it's like an L2 norm squared. This is what we call the loss-based dissimilarity or risk-based dissimilarity. And you can establish a rate of convergence, and we have proven that it converges at rate n to the minus 2/3 up to log n factors, which is remarkable because it's almost dimension-free. So whatever the dimension is, the rate is n to the minus 2/3 up to a few log n factors. So that's, firstly, that's faster than, this will correspond to a rate of convergence of n to the minus 1/3. We only needed n to the minus 1/4. So this gives us the guaranteed n to the minus 1/4 for TMLE. So now we can say, as a consequence, a TMLE that uses an initial estimator, an Hull, a highly adaptive lasso, or a superlearner, including highly adaptive lasso as one of the candidates. For example, in the outcome regression and the propensity score fitted with GLMnet with this very high dimensional basis, then we will be asymptotically efficient because the condition is now true. It's n, the remainder is n to the minus 2/3, which is faster than n to the minus 1/2. And all we need to assume about our statistical model is that these true functions, the propensity score and the outcome regression, are cadlag functions. They can even make jumps, right? They don't even have to be smooth. All they need to have is finite variation. They cannot get endlessly crazy. That's all. So it's kind of truly saying that asymptotically we can construct efficient estimators essentially without assumptions. Only this type of assumption, which is a very weak smoothness assumption. And so, for example, for the AT, it comes down to saying that the TMLE, which uses initial estimated highly adaptive lasso, is asymptotically efficient under, of course, the positivity assumption. You need your parameter to be identifiable. So that's what you need the probability on being treated for every stratum to be positive. And if it will be an average stream effect, it also should be smaller than 1. And you need that these true functions you need, which is the outcome regression and propensity score, need to be cadlag and have finite sectional variation. So it's a very weak condition. Then we have an asymptotically efficient estimator, and thereby also have valid inference, valid confidence intervals, 95 coverage, type 1 error, open 05, all asymptotically now nilled. Okay, where are we? Okay, so now we get to the second order TMLE. And so what's the idea here is to say, look, this first order TMLE still depends on the initial estimator. And we talked about the initial estimator better be good, right? Like the superlearner using highly adaptive lasso, true. But nonetheless, it matters. And so the question is, how should we tailor the initial estimator in the TMLE to make it optimal for its purpose? Its purpose was not estimating the density. Its purpose was that it's going to be used as a plugin. So you do the TMLE update of that initial and plug it in Psi. So really, this initial estimate is used in this way. So it's like a new plugin parameter. It's this Psi evaluated at the TMLE update when you use as initial P. So then I say, this itself can be thought of as a parameter. It's a data adaptive parameter, fine, but it isn't a parameter, it's a function of P. So therefore you say, why don't we use as initial estimator for P the actual TMLE of this plugin parameter, so that we actually tailor this fit for the purpose of what it's supposed to be used for. So it makes sense to use as initial estimator in the first order TMLE, the TMLE which targets this parameter, which is like essentially like a derivative of the first of Psi. Because it's Psi at something which goes away from P in a direction which is the steepest direction. So in this way, the initial estimator is tailored towards its goal to estimate the way we're going to use it. So that's the idea of second order TMLE. Now there's a little twist here, because for that we need this parameter to be pairwise differentiable, so that there is a canonical gradient. And it's almost this. It's very smooth. When you fix epsilon, it's beautiful smooth, no problem whatsoever. The only thing is that when you do this, the epsilon is replaced by the maximum likelihood estimator. The maximum likelihood estimator uses the empirical mean. That causes a little lack of pairwise differentiability. Even though it's kind of a smooth operator, it's using the empirical causes trouble, because for pairwise differentiability you need that dpn over dp exists. So you make sure that's true. So therefore, to really push this still forward, we are going to replace in this MLE step, instead of doing the arc min over the empirical log likelihood, we're going to make it a Hull smooth log likelihood. So we take the mean over the empirical, the Hull fit, the highly adaptive Lasso fit of the density of the data. And the good news is, if, for example, it involves like an empirical distribution of the covariates, because that's what you're normally, then that one will also be used in the TMLE because it's not targeting that. And then you can still keep that. So you don't have to, it's really only going to matter doing the hull for the outcome regression, the propensity score. So you can just, because we still would have this property as long as the TMLE is not changing things and just sticks to also being the empirical. So for these parts, there is completely, this can be set to the empirical. It's only for the things, the parts of the density which really are going to be smooth. That's where you need then to use hull. And this can be made very close, arbitrary close. You can even verify it to the actual empirical MLE by just undersmoothing hull, because hull is an MLE. It is almost a non-parametric MLE, right? It's just using the L1 arm, and you can just increase the L1 arm until this is very close. And that's called undersmoothing hull, and that gives you then essentially equivalence for all practical purposes in a completely controlled way. And so by now, our parameter, which is this fluctuation parameter, which is nothing else than psi evaluate at the TMLE update, is now pairwise differentiable. It will have a canonical gradient. It will have an exact remainder. And so it's like we're back to doing TMLE. So we can now say, okay, I'm going to replace my initial estimate in the first order TMLE by a TMLE of this parameter, this updated parameter. So we construct a least favorable path, and we're targeting precisely what we know is relevant, what we need to tailor it for. And then we get, for the initial estimator P, we get a TMLE update targeted towards this fluctuation parameter. And so that becomes then the TMLE. And it will solve now the empirical mean, smoothed empirical mean, because we use the smooth log likelihood. It will now solve the empirical mean of this new canonical gradient. We call a second order canonical gradient. And then the second order TMLE is nothing else than use the first order TMLE update of this TMLE update. So you have now, this is a TMLE, that becomes the initial estimator for the next TMLE. And that's called the second order TMLE. And all it is, it's a first order TMLE, except with the initial being targeted towards what it's used for. And then the corresponding plugin is, of course, this. And that's the second order TMLE. Now that second order TMLE has, again, crazy finite sample property, because what we can show, right, we can define, suppose you use a first order TMLE, right? Then we know that plug-in minus true behaves like this empirical process of this is the canonical gradient at the essentially P0, is the TMLE update at the correct P0. So this is kind of remainder for a first order TMLE. Why don't we really, wouldn't it be nice if we can set the initial so that this remainder for the first order TMLE relative to its linear approximation, empirical mean, is minimal? Right? This is normally second order, but can we just say, let's minimize it? So what is this term? You can actually show it equals precisely the terms, again, you have to worry about. It's the exact remainder in the TMLE, and then also this empirical process difference. So we like to choose the initial P so that this is minimized. So let's just play Mr. Oracle. Let's just act as if we can do that. Okay, so this is the thing we want to optimize in P. So let's do it, right? So, and also what you can see here, that this first order, this total remainder I just defined, can be expressed in terms of that fluctuation parameter we were targeting. So it can be expressed in terms of this minus that plus that. So now you see that this exact remainder, which we really like to choose the initial estimator so that it's minimized, is precisely up till a constant, because this is all P0, our fluctuation parameter, the one we were targeting. So that's where you start now seeing, if you do the TMLE of this, you're essentially doing the TMLE of this. And that's why you get this story, and this is just a little extra remark, that what actually mathematically happens is that the exact remainder after doing the targeting becomes now an empirical process of a second order efficient impulse curve plus a new second order remainder, but of the first order fluctuation parameter, which is now third order. And then this is an oracle remainder, because this is essentially like P0 with itself, right? It's only a maximum likelihood in a correct one-dimensional model. So that's what happens in the math. But from a finite sample perspective, what we also have is that if we would optimize this exact total remainder, right, which is this one here, which we just showed is this plus that. So you like to choose the initial so that this is minimal. So then you have to optimize this. So suppose I say I started an initial P and run a steepest descent algorithm. Then I would need to know the canonical gradient of this. But the canonical gradient of the exact total remainder is the same as the canonical gradient of that up till scalar. So again, we have this property that running this oracle steepest descent algorithm, literally optimizing the exact total remainder we care about, so that we get like maybe even a third order term instead of a second order difference relative to the empirical mean of the efficient impulse curve, corresponds precisely with computing this second order TMLE, this optimizing in the initial, running the second order TMLE along this universal least favorable path, except again, it has to stop when the likelihood is maximized, because then it doesn't know which direction to go anymore. And you can actually see that again. Here is an example. Here's the exact remainder of a first order TMLE. And here's the initial estimator. When you run the first order TMLE, you move in the right direction, that the remainder gets smaller. So you get here. But then you run the second order TMLE and it moves much more in that direction and reaches this very close small value for the exact remainder. So this actually happens in a finite setting. And here's another example where, so let's say we made a case where the first order will fail because you start so far away. Nonetheless, once you kick in the second order, it still nails it and gets close to being a perfect remainder so that you can get inference and everything. Now, this is all finite sample kind of a characterization, which is kind of remarkable of what second order TMLE does. But theoretically, you also want to have some formal result, and I'm just going to keep it short because there's a lot of math. But here's the key, that the second order TMLE minus the truth behaves now as an empirical process of the first order canonical gradient plus an empirical process of the second order canonical gradient. This is just an empirical mean of this, and this is an empirical mean of that, in essence, if we undersmooth a little. And then here are oracle remainders. These are crazy remainders. It's like a parametric model. So this is 1 over n, right? Here's another 1 over n. So this is all nothing. And then there is this guy. So the only remainder we deal with is this guy. And what is that? That's expressed in terms of the exact second order remainder for that fluctuation parameter, which we know is third order. So this actually happens to be a difference of 2 third order differences, and you can actually express it in terms of the exact difference for the actual parameter psi, but then iteratively targeting the initial. And so this is an exact expansion showing that we now can approximate our estimator minus truth by an empirical mean of a sum of 2 influence curves, this plus that. This is already going to 0, so that's why this will be negligible asymptotically, but in finite samples, it can really help. And then a third order remainder. So now we have made inference, instead of relying on second order remainders to be small, only third order remainders have to be small. No, and of course you say, yeah, but what about these smoothed empirical processes? You know, we don't like that. We would like to replace them by actual empirical. So you want this to be small and you want this to be small. But again, by just undersmoothing Hall, you can do that. And then you control that. And you can even know how to control it. However, for practice, things are actually even nice. And we can show that it's even better. What you really can just do is say, you know, forget the whole doing smooth MLE. We needed that only to get the right canonical gradient. So we now have the right paths, but we are still going to use an empirical MLE for these 2 steps, both the first order and the second order paths. That's actually the right thing to do, and it will even make it smaller. So then you don't even have to worry much less about the undersmoothing Hall. So you get a bias term which hardly requires undersmoothing Hall now. And also it's easier in practice because now, I mean, you still need for the canonical gradient, the second order, you still need this to understand this, but it's, at least from a carrying out, it becomes literally like a regular TMLE with just 2 directions. So that's what we call the empirical high order TMLE. Now, the point of this is, well, in particular, that we now can do inference, incorporating both influence curves. So you can compute this sample variance of this, which will be larger than just this one. So it will capture essentially the kind of second order inference. And then there will be this third order remainder. Now, if you use Hall, this literally behaves like 1 over n. And so on top, we can also you know, make it a little better and find samples by having bootstrap. But all this inference now ignores is a third order remainder instead of a second order. So we're moving in this way to finite sample inference. Now, you can generalize this result by saying, hey, you know, that second order TMLE used an initial estimator as well. right? And then it did a TMLE update, and then that one was the initial for the next TMLE. What about iterating that? Why not make that initial estimator targeted towards its goal where it's plugged in? And then you define this so-called second order fluctuation parameter and do a TMLE for that. And the same thing applies. And now you get a triple TMLE iterated. First on TMLE targeting that second order fluctuate round, then that becomes the initial, and then and so on. So if you do that, and that's this iterative TMLE you see here, starting with an initial estimator, first use here a TMLE targeting the cave order fluctuation, then a TMLE cave -1 order, at which use that as initial estimate, and so on. Now you can prove that this plugin TMLE with a very targeted initial estimator, because it involves already this sequential targeting, behaves now as a sum of k empirical processes with this first order influence curve, second order, third order, and these higher order influence curves already, like the second order is 1 order difference, the third order efficient influence curve is actually a second order difference already. So this becomes smaller and smaller when we move up J. But nonetheless, you can incorporate them in the inference because this is all one big empirical mean. These are oracle remainders like a 1 over n. So all we have left is this remainder, but that one is in k+1 order difference. It's like an integral of some estimate minus p0 to the power k+1. And so that's the generalization for k+1 order. And then I'm going to conclude with some simulations. This is actually for the ATE, where we did some simulations where we made the initial estimator of propensity score n to the quarter. The outcome regression is inconsistent. So now we have a TMLE which has a estimate of propensity score which is consistent but only n to the quarter. The initial estimator is inconsistent. So the first order TMLE should now have a root n scale bias that increases with n. So in other words, it shouldn't allow for formal inference asymptotically, and it should have real problems for inference purposes due to the bias not disappearing once you blow it up with root n. And that's what you see. The bias gets larger and larger. It's not shrinking. On the other hand, if you use the second order TMLE, you see this bias being much smaller, right? 0.72 to 0.078, 0.99 to 0.02. So you see this bias shrinking to the level that it becomes negligible, which is the only purpose you worry about, with respect to the standard error. And that's what matters, because if bias divided by standard error is like smaller than 1 over log n, it plays no role anymore, and the inference can be purely based on variance estimation. And so here you see that inference is saved by using a second order TMLE, in a case your initial estimate is not nailing it. And here's another one where both are n to the quarter. The first order TMLE should now have root n scaled bias that does not go to infinity, but it still doesn't converge to 0. But the second order TMLE should now still be fine, because it will be third order difference. And so when you blow it up with root n, it will be, so n to the -3/4 times root n still should go to 0 as n to the -1/4. And so that's, again, you see huge reductions in bias by using a second order TMLE, and the ratio of bias divided by standard error becomes negligible, which allows you to get formal inference. Now, the integral density squared is kind of an interesting example, because there the exact remainder is an integral of an p minus p0 squared. So this is a kind of non-forgiving remainder. So if you do first order TMLE, you have to deal with this remainder. It has to be negligible, otherwise your first order inference is biased, because this always adds a negative term. It doesn't matter, it always gets squared and integrated. So that's really hard problems, to get inference in problems where these exact remainders, no cancellation happen. Like in the ATE, it's beautiful. It all cancels out because there's an integral of, propensity score minus true propensity score times outcome regression, which are even orthogonal factors of the likelihood. So there's a lot of canceling going on. Here, there's no canceling. Every different, not succeeding in nailing P0 at any point gives a contribution. However, if you use second order TMLE, this guy goes away, and it becomes a third order. Now, third order has already cancellation. On top, it's third order. So it's a whole huge difference. Now, and here is our simulations for that, where you see here bias, and this is just a range of simulations where we make essentially the initial estimator more and more biased. And you see here that this is second order TMLE using some undersmooth Hall. This is the second order with empirical. They're all doing great in bias. If you use first order, you really have this bias becoming an issue. That's what you see here. Bias divided by standard error starts going up, and eventually will get larger and larger. While for the second order TMLE, it just nothing like that is happening and everything is good. And here you can see some numbers, right? First order, here a little difference, and then here a whole order of difference. And we should be undersmoothing, and that's what you see. This is not doing the undersmoothing, so then you have still this bias term due to the whole smoothing, but you can correct for that, and then you see now a big difference. First order is 1.7 10 to the minus 3. This is now 10 to the minus 4. And similar here, you have 2 times 10 to the minus 3, and it becomes 5 times 10 to the minus 5. So that's the huge difference in bias reduction. So I'm going to conclude with some remarks. So the cave order TMLE allows a linear expansion of a remainder that is incapable of one order difference. Dramatic reduction in bias due to second order TMLE are already observed in simulations. It not only weakens the assumption on the initial estimator for asymptotic efficiency, but has a clear finite sample impact on bias and improves coverage of confidence intervals. And we also have that finite sample property that it corresponds with literally with running a steepest descent algorithm. So it literally helps. A particular appealing an estimation problem in which second order remainers are behaving as square differences because they're non-forgiving, and so you really pay a price in finite samples. Higher order TMLE also opens up the road for inference in problems in which the first order efficiency curve disappears, which are problems where that happens, like some testing some null, and then the first order efficiency is gone. So how do you still do inference then? That's where you kind of need that higher order efficiency curves as approximation. And so this kind of stuff might be very helpful there. Now we're also working on pure computational methods for calculating the second order efficiency, third order, and so on, so that this all can be done with algebraic techniques like Cholesky's decomposition and so on. So it all becomes then essentially a computerized higher order TMLE. So I end here, and thank you for your attention.
Thanks. Are there any questions? Okay, if there's no questions, then thank you very much for a wonderful talk, and we will see all of you next week. Next, we will be in person is an announcement for U of M folks. Okay, all right, take care, everybody.
Thank you.